This video cast is for Chapter 13, Properties of Solutions. Don't watch the video cast unless you have your PowerPoint handout for Chapter 13, Properties of Solutions with you. Solutions are homogeneous mixtures of two or more pure substances. Homogeneous meaning the same throughout. In a solution, the solute is dispersed uniformly throughout the solvent. Generally, we say that the solvent is present in a greater amount than the solute, although this isn't always the case. It usually is. Notice the different states of solution and states of solvent and solute there can be. It's not necessarily just a solid that is dissolved in a liquid. It could be a gas in a gas, or a gas inside of a liquid, or it could be a liquid inside of a solid. All of these types of things mixed together in a homogeneous way could be solutions. The intermolecular forces between solute and solvent particles must be strong enough to compete with those between the solute particles and those between the solvent particles. So to make the solution, the two types of particles must be able to, in effect, separate from one another and form a new bond or attraction between the two. So how does a solution form? As a solution forms, the solvent pulls solute particles apart and surrounds or solvates them. In these pictures, you can see the water molecules, the the red and white ones, surrounding this ionic compound, let's say it's sodium chloride, and surrounds each one of the particles. Here the negatively charged oxygens surround the positively charged sodiums. And over here you can see that the positively charged hydrogens would surround the negatively charged chlorines. If an ionic salt is soluble in water, it's because the ion-dipole interactions are strong enough to overcome the lattice energy of the salt crystal. You can see here that the positive ends of the water molecules surround the negative chloride ion. Energy changes to make or in a solution. Simply put, there are three processes that affect the energetics of the solution-making process. First, there is the separation of the solute. Second, there is the enthalpy, that is the separation of the solvent. And thirdly, there is a new interaction between the solute and the solvent, making the new solution. Three processes, three enthalpies, H1, H2, and H3. The enthalpy change of the overall process depends on the enthalpy change for each of the steps. Things do not tend to occur spontaneously, that is, without outside intervention, unless the energy of the system is lowered. Yet, why do sometimes some endothermic processes occur? If you look at this enthalpy diagram, you can see that the first two enthalpies, H1 and H2, take more energy than the third portion of the solution making, the attraction between the solute and the solvent particles, therefore making a net endothermic process. We know that some solutions still form even though the process is endothermic. In other words, it does not give off energy. Like the dissolution of NH4NO3 in water, heat is absorbed and not released. Why does something like this happen? Well, enthalpy is only part of the picture. The reason is that increasing the disorder or randomness of a system tends to lower the energy of the system. This increase in disorder or randomness is called entropy. Entropy. We'll learn a lot more about entropy and the mixed upness of a system in chapter 19. But for right now, it's sufficient to know that if you have two separate substances and you mix them together, they're going to become more random or more disordered, and it is the tendency of the world to become generally more random or more disordered, and therefore can be a driving force in causing a solution to form. Since enthalpy is only part of the picture, even though enthalpy may increase, the overall energy of the system can still decrease if the system becomes more disordered. And we'll actually learn a new equation about this in chapter 19, where we take into account both the enthalpy and the entropy, the randomness or disorder of the system, and be able to determine whether or not a solution or some other process will spontaneously occur. Students, please beware about this unit on solutions. Just because a substance disappears when it comes in contact with a solvent does not mean the substance is dissolved. Dissolution is a physical change. You can get back the original solute by evaporating the solvent. If you can't get the original solute back, that means the substance didn't dissolve, it reacted and formed new things. So when you take sodium chloride and dissolve it in water, if you evaporate the water, you can get the sodium chloride back. That was a solution-making process when you took the sodium chloride and put it into water. But if we took the sodium chloride and we put it into something and we evaporated it and we could not get the sodium chloride back, be careful. It's not a solution-making process. It's something that reacted. Beware of that. So let's look at the different types of solutions. The first one is called a saturated solution. This is when the solvent holds as much solute as possible at that particular temperature. Dissolved solute is in dynamic equilibrium with the solid solute particles. In a saturated solution, when they say dynamic equilibrium, they mean that these, for instance, chloride and sodium atoms, or ions, that are surrounded by water, spontaneously form back together to form sodium chloride, but at the same time, new ones are surrounded by water molecules and replace them. And so even though they might be changing, there's still the same amount of sodiums and chlorides dissolved. In an unsaturated solution, less than the maximum amount of solute for that temperature is dissolved in the solvent. More could be dissolved. In a supersaturated solution, the solvent holds more solute than is normally possible at that temperature. These solutions are unstable, and crystallization can usually be stimulated by adding a seed crystal or simply scratching the side of the flask or agitating the supersaturated solution. You can notice in this picture it looks like it's a stable solution, but once a seed crystal is added, it forms spontaneously much of this solute that's dissolved in here, there's too much of it dissolved in there, and you can see the solid forms. We'll do a demonstration like this in class. What are the factors affecting the solubility of something? Chemists like to use the axiom like dissolves like. Polar substances tend to dissolve polar solvents. Non-polar substances tend to dissolve non-polar solvents. So like things, polar, dissolve like things. Non-polar, dissolve non-polar things. The more similar the intermolecular attractions, the more likely one substance is to be soluble in another. So you can see here, these are ethyl alcohol molecules. They can form hydrogen bonds with one another. and therefore they can form good hydrogen bonds with water, and so they're quite soluble in one another. Ethyl alcohol and water are like dissolves like, both hydrogen bonding, similar size molecules. Glucose, which has hydrogen bondings, is very soluble in water, while cyclohexane, which has only London dispersion forces, is not. You can see here is cyclohexane. At each corner of this is considered to be a carbon atom. And you can see it in this structure as well. The black are the carbon atoms. It's a non-polar ringed structure, and therefore it does not dissolve in something that's polar like water. Whereas glucose, you can see, has a number of OHs around the outside. The OHs, of course, are available to form hydrogen bonds, and therefore it's very soluble in water. Vitamin A is soluble in non-polar compounds, like fats. If you look at the structure of vitamin A, you do not see very many places where you see any place where there is a possibility for hydrogen bonding, except for maybe way here at the end. But throughout most of it, it's fairly non-polar. Vitamin C, on the other hand, is very soluble in water. And you can see it has 1, 2, 3, 4 areas here, and even a couple of oxygens right here with unshared electrons that are available to bond with water, or the polar nature of water. In general, the solubility of gases in water increases with increasing mass. Larger molecules have stronger dispersion forces, and you can see here that krypton is more soluble numerically than nitrogen, for example. Gases are kind of in a class by themselves when it comes to dissolving in water. Generally, the bigger they are, the better they dissolve. The solubility of liquids and solids does not change appreciably with pressure. The solubility of gas in a liquid, though, is directly proportional to its pressure. And so if you squish a gas down into a liquid, you can dissolve more of it in the liquid. This is how they dissolve lots of carbon dioxide into your soda pop and give it its sharp, bubbly taste. This process is governed by something called Henry's law, where S sub G is the solubility of the gas and K is the Henry's law gas constant for that gas in a particular solvent, and P sub G is the partial pressure of the gas above the liquid. Generally, the solubility of solid solutes in liquid solvents increases with increasing temperature. How does temperature affect solubility? Well, if it's a solid, heat it up and it will dissolve better in a liquid. As you can see, NaCl becomes more soluble as temperature goes up. Lead nitrate dissolves more in 100 grams of water as temperature goes up. The opposite is true of gases. Carbonated soft drinks are more bubbly if they're stored in a refrigerator. Warm lakes have less dissolved oxygen in them than cool lakes. Solubility of gases is inversely proportional to temperature. In other words, the colder you get, the more oxygen will dissolve in the water. That's why fish like trout like to live in cool streams. There's more oxygen dissolved in the water and they can live better. We'll pick up with the second part of this video cast on ways of expressing concentration of solutions.